Thank you for inviting me to come back. I was here 5 years ago, and we told you what we were going to do with the James Webb Space Telescope, and now we have done it. So we are so thrilled to be able to tell you this story today. It is clearly a demonstration of international cooperation. What we see on the screen here is a picture of the telescope. It's a great golden hexagon, a mirror coated with gold. It's in outer space now. It is 6.5 meters in diameter. It's protected from the heat of the sun and the earth and the moon by this 5-layer sunshade that you see underneath it. It looks like a piece of plastic here. It's actually as big as a tennis court. This is a project that took 20,000 people to do over the course of many years, starting, in my case, since 1995. So a tremendously difficult thing, but also enabled by government support from the United States, Canada, and Europe for all that period of time. So it is possible now to demonstrate that hugely difficult, nearly impossible international projects can actually be accomplished. So I want to show you what we are able to do now with the telescope. Let's see if I can try my little clicker out and make the next slide appear. So beginning with the Cosmic Background Explorer satellite that was mentioned in the introduction, we made a map of the Big Bang. This is the picture of the sky as we observe it with millimeter wavelengths, and we see the hot and cold spots that were mentioned in the introduction. These represent density variations in the Big Bang material. So it's the sky as it was formed about 400,000 years after the expansion of the universe began. So if we believe we understand what that is, it tells us that gravity operating on the primordial density variations of that material was able to stop the expansion of material, pull it back into galaxies and eventually stars and planets, and here we are because of those very spots. When Stephen Hawking saw this picture, he said it was the most important scientific discovery of the century, if not of all time. Now we can say we think we understand a little bit why he said that. Number one, we're here because of the spots. Number two, most of them come from something astronomers can measure but cannot see. It's called cosmic dark matter. And number three, if we really understood quantum gravity, which we do not and maybe never will, we would be able to predict how much that should be. So the beginning of our universe represented, and now we ought to be able, if we think we understand that, to predict what will happen next, which is nearly impossible to predict. But let's try. So how do we do it? Well, actually, it's easier to take a picture. So we built the Hubble Space Telescope. It is now 32 years old. It is still working beautifully in space, but that's because we were able to send up astronauts 5 times to make it better and actually to repair the focus error that we had when we launched it. So an extraordinarily complex process which proved for the first time the value of astronauts servicing space telescopes, because it's still going because of them and the space shuttle program that we had, but no longer have. So the Hubble Space Telescope told us what we should do next. And they said, a committee wrote a little book, and they said, please build us another telescope that can see even farther out into space, farther back in time, tell us how the first galaxies grew and everything that happened after that. So here is the telescope on the rocket going up into space from French Guiana. This is a commercial rocket called the Ariane 5, and it's from French Guiana because that's actually a part of France. And we got a perfect launch. They did a beautiful job. And they did it on Christmas morning, just December 25th, 2021. And they did such a perfect job that we now think we should be able to have a 20-year flight operations. So, okay, where did we put it? We put it in orbit around the Sun-Earth Lagrange point. This is a place 1.5 million kilometers from the Earth in the opposite direction from the Sun, so it's overhead at midnight. It's a place which is semi-stable, so you can keep an orbiting spacecraft out there for years and years with only a small amount of thrust from the rockets. It's a great place to put a telescope because it keeps the telescope cold. It doesn't get any farther from the Earth. It's easy to communicate with it, and anyway, and we can see it every day. So we put it there. It's orbiting around, and this is what we did with the observatory after we launched it. Let me see if the movie will play. So this is the telescope as it was when it was folded up for launch. The first thing we had to do was, soon after launch, was to unfold the solar panels so we'd have electrical power. Then we had to unfold the antenna that we used to talk back and forth at a high data rate to the Earth. Then we had to unfold the giant panels that hold the sunshade. And then we have to push the sunshade out. It becomes a giant kite-shaped shape. Then we had to unfold the telescope itself. And finally, although we don't have that in the movie, we have to focus the telescope. It took many, many months. It took altogether 6 months after launch before the telescope was completely ready to operate. So in particular, those golden hexagons are not in the right place when we launch, and we had to learn how to focus them afterwards. As you see, we unfolded the solar panels. That happened within a few moments of the launch. Here comes the big panels that hold the sunshade. You look at this and you see this is an incredibly complex mechanical engineering job, and it has to work perfectly because there is no hope of getting an astronaut out there to repair it in case of a problem. Robotic servicing will become possible. It is not possible yet. So we had to be sure that it would work. To make sure that it would work, we had 4 rounds of testing of the unfolding sunshade. We had 3 rounds of testing the telescope with just instrument packages, and then another round testing it in Houston in the giant vacuum tank. There, during the Hurricane Harvey, we had 50 inches of rain falling on the outside of the building while the telescope was perfectly protected in the vacuum tank. At any rate, here you see the 5 layers of the sunshade being separated. This is all done by a very complex mechanism of cables and pulleys and one big motor in the middle. The last step, as you now see, is the unfolding of the telescope itself. So it's a standard called the 3-mirror anastigmat optical design. It gives an excellent optical performance. In fact, it is so excellent that the images are much sharper than we hoped and promised that they would be, and we are really thrilled with it. Anyway, there it is in outer space in a view that a human will never have, of course, because the telescope is in the dark. Okay, so what are we going to look at? Well, the telescope is designed to study 4 different scientific themes. What is the first thing that happened after the Big Bang? How did the first galaxies grow? It's unknown. We have many, many predictions. We have some observations made with the Hubble Space Telescope and a few new ones, which I'll show you today, that we're just beginning to understand. How do the galaxies grow? We think that galaxies are pulled together by gravity from thousands of small pieces. So we can tell that story by looking far out in space, far back in time, to see how they were a long time ago. In the lower left corner, we illustrate that we can study the birth of stars inside dust clouds nearby. And finally, in the lower right, the image suggests that we're going to study planets around other stars, which we are doing. So here is one of our first pictures. This is the one that President Biden released on July 11th. This is called the SMAC 0723 cluster. So in the center of the picture, you see extremely bright, relatively nearby galaxies. And they're very bright, and they have so much gravity, so much mass in them, that they're able to curve space and bend the light rays that come from distant galaxies behind it. So you see in the picture there are a number of strange-looking shapes that are not like ordinary galaxies. They are stretched out into arcs of circles, and that's because the gravitational forces are magnifying these distant galaxies and making them 5, 10, even sometimes 100 times bigger than they would have been without that help. So the picture is full of these galaxies. The individual stars that are nearby are the ones that have the spike sticking out. That's due to the diffraction of light. So now what do we do to understand all the things that are in here? Well, obviously we now have the shapes, but we also want to know what about those arcs? So this, for instance, said, well, let's see there's an arc over there on the left side, and it looks like they might almost be connected. So the question was, are they the same galaxy? So the answer that we get is, well, spread out the light of those things into a spectrum, see if they have the same spectrum. The answer is yes, they do. They have emission from oxygen and hydrogen, and the wavelengths are the same. So these seem to be the very same galaxy imaged twice. We'd like to know how far away are those galaxies and what's in them. So we have another piece of equipment. This one is called the NIRSpec. It came as part of the European contribution. We can identify particular tiny specks on that big picture and say we'd like to know more about them. So again, spread out the light into a spectrum, measure the constituents, and we see here hydrogen and oxygen primarily. And however we see, the patterns are shown up at different wavelengths. And that's because these different galaxies are going away from us at different speeds, which corresponds to different distances and different ages of the universe when they were being visited, and when we see them. So there they are. We're looking farther back in time than we were ever able to do with the Hubble Space Telescope. So we can also see what's inside them, spread out that light into a little more detail. Here's the same one. It shows not only oxygen and hydrogen, but neon. So this is important for our story because the Big Bang did not give us neon or oxygen. We got only hydrogen and helium. So clearly this is a demonstration that this galaxy is already getting a little bit old. Stars have been born. They've burned through their nuclear fuel, expanded and exploded, and let the atoms of oxygen and hydrogen, oxygen and neon come back out into space. We've gotten a close-up picture of a nearby cloud of galaxies. There are 5 galaxies in the picture. The one on the left is actually quite nearby, and the telescope is so powerful that it can see individual red stars in that galaxy. The other 4 galaxies are interacting with each other, crashing together. They will eventually all form into one galaxy. You can see the splashes of red color, which indicate where new stars are being born. In the top one, we see strange jets of material coming out because there's a black hole in the middle called an active galactic nucleus. So it gets extremely hot as material orbits around it and tries to fall in. It's compressed, and anyway, we can now analyze that with this equipment. So we can get a map of the composition of the gas around the black hole by spreading out the light, getting a spectrum of every single pixel of that map, and see where the iron and then hydrogen are actually located and how fast they're going. We can even see that there are other atoms, even sulfur, way out there in this most distant area orbiting around the black hole. There are even things we see called silicates. So there is dust grains in space, which are actually interesting places because they are where new stars can be born inside these cold clouds of molecular hydrogen. So we're getting to much more detail than we ever had to be able to tell our own story. How did the big universe turn into galaxies, stars, planets, and people? So here's just a beautiful galaxy. This is called the Cartwheel Galaxy, and it has this shape because a small galaxy passed right through the center of the big one and made a splash. So we can see from this the effects of splashes of galactic gas being pushed outside and forming new stars. This is the image processing for a different galaxy. The person processing this has managed to emphasize the shapes of and show the holes in the galaxy. So you see these big holes. These are places where stars have recently been born, and the heat from those new stars has been pushing out the material that was there. So we now see this thing. It looks like a slice through a sponge, and that's because of the pressure of the gas created by these new stars. So I show you here mostly just because it's beautiful. We have this one, which is a place where stars are definitely being born inside, and we can see them. This is a place called the Carina Nebula. The stars at the top half of the picture are new ones, very bright and mostly quite blue. They are producing so much heat that they are beginning to evaporate the surface of the dust cloud, and you see the blue wispy material coming up from the cloud. And then we're looking inside, and we see strange and interesting shapes due to the motions of material there. We've gotten a nice picture of this one. This is a pair of stars. One of them has exploded, or partially exploded. and send off its outer layers of its surface into a cloud of material around it. When the sun is old, and it's about 5 billion older than it is now, the sun will do the same, as it will expand to fill the size of the Earth's orbit, and it becomes unstable, and little puffs of material will keep coming out. This is the future of our sun, sometime. But don't worry, it's a long time. This picture on the right actually shows, for the first time, that the star in the middle that did this is double. So there are two of them in there. The one on the left, that's sort of redder, is now visible because we have the infrared capability that can see through dust clouds. Seeing through dust clouds is because of the diffraction of light. When you go down to the airport and they examine you through their millimeter wave scanner, it's because long wavelength can go around dust grains or obstacles, while short wavelengths will just bounce off. So the other star in the middle there is also going to blow up sometime soon. That'll be a very different, interesting picture. We take pictures of everything in the solar system, and we're just beginning to get pictures. This is a picture of Jupiter, and you can see it looks different when we take an infrared picture. And we're especially interested in a few things. One is there's a ring. You can just barely see it. It's a very faint ring around Jupiter. It has a ring also. It's not nearly as bright as the one that Saturn has. We see the surface of Europa. Europa is a satellite of Jupiter. There are 4 of them that were discovered by Galileo himself. And we're very interested in Europa because of the potential that it might be alive. So here is a picture close-up of Europa that we took with a mission we called Galileo. And you see that it's covered with ice. And under the ice is a liquid ocean, as we know from measurements of magnetic fields and things. And we've fairly recently seen with the Hubble Space Telescope that water comes spitting out from the cracks between those blocks of ice. When we first knew that there was an ocean there, we said we're going to need to melt our way in with a nuclear reactor to find out if the ocean is alive. Now we don't have to do that. We just have to analyze the water that comes up from the cracks. So NASA is actually sending a mission out there to do that and fly through the water jets and measure their molecular composition. Are there organic molecules? So even if it is alive, of course, we're not expecting complex civilization, but even a bacterium is quite complex. We will be looking at stars that have planets, and this is another one of the movies, but this one we don't have to worry about. I'll just tell you about it. The planet in the upper left will go around the star, and once every orbit, it will block some starlight. The idea here is that at some wavelengths, where there's something in the atmosphere, like water or carbon dioxide or something, the planet looks a little bigger and it blocks more starlight than at other wavelengths. So we can now tell how much light is going through the atmosphere of the planet if it has an atmosphere. So we're going to try this on many, many planets. And we've already examined one, which I'll show you in a moment, and we know that it has water. So, of course, the bigger question is, are there any planets out that are like ours? And that's a pretty hard question. There's the spectrum that we got showing the atmospheric composition of a large planet, actually quite a hot one, orbiting a star like the sun. This planet is about 1,000 degrees centigrade, and it's about as big as Jupiter. So it's a very big and fluffy planet, but you can see here we have a spectrum, and there are bumps in this spectrum that show how much light has been blocked by the planet as a function of wavelength. And the bumps all correspond to water molecules. So when we say water, we should actually be thinking steam in this planet because it's so hot. But we've demonstrated this way that the technique works, and it works better than we ever hoped it would. So we're now in the process of examining small stars and small planets like the Earth could be. So in a little while, we may be able to tell you whether Earth-like planets, Earth-sized planets, have atmospheres around other stars. So all astronomers can participate in our project. The original nations that built the telescope said, that's great, we're glad to have access to the telescope, but anyone can propose. So if you are a scientist at any institution from Azerbaijan to Zanzibar, you can propose, and there will be a call for more proposals due in January. So we've already got many scientific programs chosen to release their data right away, so you can find them if you just Google JWST-ERS, that's Early Release Science, you can find them all. There are archives at the Mikulski Archive at the Space Telescope, and the data become public through there. Anyone can get an account and download the data. So everything's working. If you're a computer scientist, then you're probably happy to know that we are using Python as a very popular language for doing the analysis. So, by the way, we do not know who you are when we read your proposal. So you can be a graduate student and still win. Almost 10% of the proposals that we chose were led by graduate students. So I think that's my main list of stories to tell you this morning. Anyone can follow along. Of course, we're making the news all the time. We're so proud of that. Our team is proud of that. And I would say, to quote our project manager, none of us are stars. We are all in the team together. We are proud of our work together. We have proven that you can do the most amazing things when you combine forces and keep at it. So thank you for inviting me, and I have some time for questions. Well, usually what we do, since infrared is invisible to the human eye anyway, we say we'll do something like we do with ordinary light. The shortest wavelength will be blue, the middle wavelength will be yellow or green, and the longest wavelength will be red. So we have many filters. We take different pictures and we assemble them into a composite color. That's usually what we do. Sometimes we have a color filter on the camera that says, I'm only going to observe the wavelength that comes from a particular atom or a particular molecule. So then it's not exactly the artificial color that you would expect, because we're showing in a kind of graphic way what kind of atoms or molecules are where. So it's different. So we have to explain each one separately because they're always different. But that's generally what we try. We need to make it beautiful, and we need to make it meaningful. So how do you point at something? Well, number one, there's no ground in space to stand on to turn. So what we do is we have rotating wheels. So we have a big wheel that turns, and if you want to turn the telescope that way, you turn the wheel the other way. So conservation of angular momentum tells you can push on something as long as it's on bearings and spins in your telescope, you can push. So that's how we point at things. On rare occasions, we actually fire the rocket jets. When the wheels are spinning too fast and can't spin any faster, then you fire the rocket jets. Okay, so how do we keep it going for a long time, basically? Number one, try to make a good design. Number two, have two of everything where it's possible. So the camera has two sets of identical, so the near-infrared camera has two sets of chips. The spectrometer has two sets of chips. So we do two of everything where it's possible. We have two sets of transmitters and receivers. We have two command processors, two computers on board, two of everything where possible. Now that's just because when you have thousands and thousands of parts, it's pretty likely that one will fail for some reason. A cosmic ray will hit it, or it will just get old. So that's our solution, is redundancy, number one. I think it was mentioned there are cosmic particles, so there are several kinds that we're concerned about. Cosmic rays, that's mostly protons and alpha particles, but some heavier ones, they come crashing through the equipment. So they hit the detectors, they hit the electronic chips, and so we have to design knowing how much that will happen. So all of the parts are tested in advance to make sure they're good enough to survive. Then there's another kind of particle we're concerned about, which you may have read about, called micrometeoroids. Little tiny grains of sand that are so small you couldn't even feel one if you had one in your fingers, 1/1000th of an inch across, just a few microns in size. They come at enormous speeds, up to 30 or more kilometers per second. And if one of those hits our mirror, we get a hole, a little hole. Usually it's not a problem. But we had one which either hit a special vulnerable spot or was very fast, and we got a noticeable bump on the mirror. Fortunately, it's already so good that that's not a problem, but eventually we will have more. We don't know whether that's just a random bad day or There are many more coming, but so far we've been very fortunate. We've only had the one big one. So many hazards. When I said that most of the spots on the hot and cold spot map of the Big Bang were from dark matter, that's because there's just not enough ordinary matter to make those spots. So we see evidence in astronomy that dark matter is everywhere, and especially the story that we get from computer simulations is dark matter pulled together the halos, what we call them, that would become galaxies. And then ordinary matter was able to fall into those gravitational potential wells and form the galaxies that we see. So dark matter is everywhere. There's a vast amount of it. Most of the matter in the universe is dark. We call it dark matter, but we should really call it transparent because it means we cannot see it. What is it? Nobody has any idea. Many experiments are being done around the world, including some in Korea, to look for the dark matter in a laboratory. So far, we have many, many years of working and no evidence of success. So we know what it's not. We don't know yet what it is. So come back in 10, 20, 50, 100 years, maybe we'll know the answer to your question. This is one of the hardest ones because we do not know that nature gave us anything to see. We do not know there's ever any possibility to finding it in the lab, but we have a chance to learn more about it all the same. I'm a cosmologist, so I really can't give you a good answer. But I would say the human body and survival in space is much harder to do than cosmology. Experiments are very slow. We put a person in space and see what happens. And we've been finding out in so many ways that it's bad for us to be in space. Cosmic ray damage, damage to our circulation, damage to our eyes, damage to our bones, so many ways for things to go wrong for us in space. So the short version is, well, don't do it. Don't do it very long. Make a quicker trip. Go to Mars as fast as you can. Go to the moon, where at least you have some gravity. Then we don't have enough practical experience to do it and do much better than yet. Why don't we have a centrifuge in space? When I was a child, everybody knew that we needed a centrifuge to keep us protected in space. Well, we don't have one. It's a very hard engineering job. If you're going to survive cosmic rays for 10 years, you need to be protected. There's basically no way to shield away the cosmic rays from the galaxy. They come in at enormous energies of a GeV or more, and they'll penetrate through many meters of shielding. So, well, you're not going to carry that on your spaceship. When you get to your destination, you can dig a hole and live in the bottom of a cave or find a cave. This is a hard problem. So when people say they're going to live on Mars, we're implying a huge engineering effort to be able to make them safe and happy. So it's a hard problem. So medical engineering to overcome some of these problems is also a hard problem. And I don't know enough to tell you, but clearly it's going to be very important. So there was another part of your question about SpaceX and the private companies. So, well, number one, I'm certainly thrilled to see that we've gotten the price of access to space to come down so rapidly with not only SpaceX, but other companies developing reusable boosters. So when you can use your booster over and over again, you don't have to build it fresh every time. And I know they like to say it's not a used rocket, it's a space-proven rocket. So there's truth in that. So anyway, things are getting a whole lot cheaper, and I'm so pleased to see that. We had immense troubles with funding. Our original concept was started off and backed by an administrator at NASA who believed there was something possible called faster, better, and cheaper. So engineers laughed and they said, that's not possible. So we did not request enough money from the beginning. We got, at least twice we got through the project and said, we still don't have enough money from Congress to do the job, and it's going to take much longer. So how did we possibly survive? Well, we had to have outside committees, outside review boards that said, basically they did a good job, but they just didn't ask for enough money. So it's not a stupid idea. Just ask for more money. If you didn't send them more money, then we can finish the job. So that was the committee reports, and Congress agreed. But they had to do this twice because the problem keeps on getting harder. When you really learn how hard it is, you say, oh my gosh, how did we miss that? The biggest change we had at the beginning was we had to change the test program. We had in mind a certain vacuum tank in Ohio that belongs to NASA, and we got to a closer look and we said, no, that's not going to work. So we better use the other one in Texas. And first we were going to have the telescope at the top looking down at the test equipment. Well, that turned out to be a bad idea, so changed the test plan. So everything about the test program was much harder than people really appreciated. So that's where a lot of the work went. But of course, when you understand that you have no chance to fix something, you have to get it right. Doesn't matter how many test programs it takes. If you're going to do this, you have to do it right. So people understood, but many people were very impatient as well. And people said many terrible things. People said terrible things. But we're so proud that we all got to do it anyway. From my heart, I'm just so thrilled that this amazing project has been possible. We have had so much support for so long, and the problems were so hard, and now we have hopes for discovering something that we never knew about, something about our own trajectory through the universe. So that's kept me going all this time, the possibility that we could know our own story. So about getting a Nobel Prize, well, the tool is now available. If you're fortunate to find something with that telescope that nobody knew before, perhaps there will be a prize there for you. The Nobels usually are given for discoveries, surprises of some sort. Building the telescope doesn't get you a prize, but discovering something unknown does. I think what's always driven me is curiosity. I want to know how things work. I think I was a curious child. I'm a curious grown-up. Maybe I'm still a child. Because I think that's the thing that makes us all in this together. We just all want to know together what happened, how does it work, and what may happen in the future. So pretty nearly every challenge that we have on a planet-wide scale has a very deep technical scientific basis, and we need to give everything that we have to that. So when we say we built this amazing telescope, we also proved that whatever the technical challenge is, we can solve it.